Good morning, everyone. Good afternoon for Dr. Savini. Today we have the pleasure and the honor of having Dr. Giacomo Savini with us. He is one of the most recognized experts in refractive surgery in the world. He works in Italy, and Dr. Savini, it's a pleasure. Thank you again for being with us, and please, you can go ahead. Thank you.
Okay, I wish to thank you for the invitation, and I was asked to give a talk about the ray tracing software of MS39 that I currently use for IOL power calculation in post-refractive surgery eyes. But since I was given the opportunity to talk about 40 to 50 minutes, right? I thought that it would be interesting to give some explanations about the reason why IOL power calculation is so difficult after previous corneal refractive surgery, and which solutions are available, not only ray tracing, but others. So I will spend some time, and especially I think that the most important thing is try to understand why errors occur in these eyes if we do not perform specific calculations. So there are three main sources of error that you can see in this slide. The first one is the keratometric index error. The second is the measurement radius error. And the third one is the so-called formula error, which regards the prediction of the ELP, the lens position. First error, the keratometric index. All devices from old manual keratometers to the most updated OCT do not measure the corneal power, the 43 diopters that we see on the printout, but they measure the corneal curvature, which is the radius, which is expressed in millimeters. And this usually happens on the anterior surface of the cornea. Of course, now we have devices able to measure also the posterior, but until a few years ago, this was not possible. So we have to find a way, and this is what the keratometric index is useful for, to convert millimeters into power. And the formula that is used by all devices is this one. I don't know if you can see my mouse. It is.
We can see it, Dr. Savini.
Okay, thank you. It is P, the power of the lens. That means the power of the anterior and posterior surfaces of the cornea is equal to n minus 1, which is the refractive index of air, divided by the radius that we measured with our instrument. And in 99% of cases, this index n is equal to 1.3375. In a minority of cases, I think just the IOL master that are sold or that were sold in Germany is a theoretically better number, which nobody uses, 1.3315. And so the keratometric index on one side depends on a constant ratio between the anterior and posterior corneal curvatures. And this leads to good accuracy in normal unoperated eyes. But you see, it's mandatory to have a constant ratio. What happens, we all know that after myopic and hyperopic EXCIMER laser, we change this ratio so that the keratometric index that was used to convert the millimeters into diopters is no longer valid. Many years ago, I published this graph showing that we may change the keratometric index and decrease it according to the attempted correction. So from the original value of 13375, it could decrease to around 1.3265 for myopic corrections up to -11. And this change of the keratometric index was published by me. And okay, the second slide, sorry, I made a mistake, was Dr. Camellin, who is another Italian surgeon, and then Dr. Harade. These are very similar equations to recalculate the corneal power with the new keratometric index. And here you see an example. You see that with this corneal topography after LASIK, you have an average of 34.33 diopters, average CIM-K. But if you decrease according to the methods that I just described, the keratometric index, the power decreases by almost 1 diopter. And so you understand that the keratometric index error is one of the main sources of error, because it leads to an overestimation of corneal power after myopic surgery. And if you overestimate the corneal power, you underestimate the IOL power and you get hyperopia. And what about radial keratotomy? Because in this case, both corneal surfaces flatten. And for many years, we have told that since they deform in parallel, the ratio is maintained and the keratometric index is still valid. This is not true, because together with Dr. Camellin from Rovigo, a North Italy city, we found that this ratio changes after radial keratotomy, because there's a more evident flattening of the posterior surface. We use the pentagon to demonstrate this. And this change is proportional to the number of incisions. And if you take a look at the graph to the right, you see that, okay, the number here is hard to, I don't know why it's hard to see, but you see that the normal ratio in healthy unoperated eyes is 1.22. This is the large majority of eyes. If you take a look at myopic and PRK, the mean ratio is 1.34, and it goes down to 1.12 in radial keratotomy. So the keratometric index error happens after any corneal refractive surgery, and is the first one. The second error is the measurement of the radius error, because when we have small optical zones that may happen after radial keratotomy, like in this case, in these cases, we would measure the radius out of the optical zone on the periphery, where the curvature is different. This does not happen in large optical zones like the one on the right, but it's a big problem in small or decentered optical zones. You see that the same measurement is taken here on the blue and here on the left on the yellow. You may take advantage of some more central measurements of different devices to take this error into account and correct it. And we found some years ago that this does not happen with optical zones of 6 to 0.6, at least 6 millimeters. Third error happens when you use the Hofer-Q, Holliday, and SRKT formulas to predict the position of the IOL, because these formulas, these older formulas, but also some newer, predict the position of the lens based on the corneal curvature. But if you change the corneal curvature with EXCIMER laser, you will get wrong predictions, because you use K and axial length to predict the position of the lens inside the eye, which is a kind of anatomical prediction. Then you use the predicted position of the lens, keratometry, and axial length to get the IOL power, which is an optical prediction. Yeah, but this happens. Look at this example. Before surgery, you had the 46, 47 diopters of corneal power, and you got the right ELP estimation. If you correct -10 with an EXCIMER laser and you go down to 37, it's logical to expect a wrong ELP estimation. And this can lead to, if you have an error of 1 millimeter in the ELP estimation, you will get at the spectacle plane 1.4 diopters of hyperopia that will add to the keratometric index in post-myopic eyes, because these errors go into the same direction. And if you have a 10 diopters correction, you will have 2 millimeters of, you go down from 6.5 to 4.5 millimeters of ELP, and you get 3 diopters of refractive error just because of the formula. This does not happen if you use the Haigis formula or the Shamas PL or the Camelin formula, which is an Italian formula. Why? Because the Haigis formula does not use the keratometry to predict the ELP. If you want to use older formula, you have to use Aramberry's double K method, where the pre-op K, if you know it, that's good. Otherwise, you have to imagine what, or to estimate it. The pre-op K, 43, 44, whatever, sorry, is used to predict the position of the lens, while the post-op currently measured K is used to calculate the divergence of the rays through the IOL. And how can we obtain preoperative keratometry if they are not available? You can either use a mean value, for example, 43.81, which was published some years ago, or you may base your estimation from the current keratometry, and you know, for example, that now you have 36. The patient tells you that she underwent 6 diopters of myopic correction, and you will get around 42 diopters pre-op K. Or you may use estimated, if you have a Shenfield camera, you know that the mean ratio is between the anterior and posterior surface is between 1.21, 1.21, 22, as I told you before. Then you measure the back radius, you multiply by 1.21, and you get the anterior estimated preoperative radius. And this is just an example. Or you may rely to a paper we published in 2016. If you have a pentacam, you can take advantage of the posterior corneal radius and the posterior Q value and get a good estimation. This is what I usually do. So you take the back radius, the back Q value, and you enter this in the formula. And what happens if we do not correct the calculation formulas? In cases of myopic, LASIK, and PRK, you get a hyperopic error, around 1 diopter every 3 diopters of myopic correction. And the opposite happens if you have, this is an error, in case of hyperopic, not myopic, LASIK and PRK, you get a myopic error. Is there any question before I go on? Or is everything clear?
Okay. I think this was a very good overview of the problem, Dr. Savini. So anybody in the audience has any questions? Okay, it seems that everything is clear.
Okay. By the way, you have my email, and any question, we can also discuss it, talk about it later.
Perfect.
So which is the big problem. It is that there are more than 30 methods to do calculations in these eyes, and such a big number may generate confusion rather than accuracy. Many people go to the Ask Us website, but the Ask Us website gives too many values, and you don't know if you have to use the average, the lowest, the highest. I don't like this approach of so many methods without an explanation on which is the best one. So we have to think to our patient and to the data we have. So there are methods that should be used when all the data before and after LASIK are available, when only some of these data are available, or when we do not have anything. We published a series of 3 papers at least, where we compared formulas. And in 2015, before the Barrett True-K formula was released, we came out with this decision tree, which is now available, and I can send it to you by email as an Excel file. I did never use it, I never did a website because I should ask the permission to too many people, and I did not have time. But I can send it by email, a simple Excel file. And how does this work? And this is, I repeat, this is based on a paper that we published, so there is some evidence. Well, do you have the original keratometry? Yes, you have. Okay, go to the left, because it is available. Do you also know the pre-LASIK spherical equivalent, or the correction that you did? Yes, you know. Then the best formulas are the double K Savini, which means the one with the adjusted keratometric refractive index, with the SRKT. And the second best one was the masked, and the third one was this called Sites Spiker Savini, which I later called in other papers triple S. Or maybe you have it, but you are not sure about the power that was corrected by the laser, and so you go here. Or you don't know the pre-LASIK K, and you go to the right. If you know the refractive change, you stay here, or you go to the right. Then in a later version, I also added some no-history methods available for the Pentacam. But there are now some better methods, or at least, I cannot say better, easier, because you don't have to spend time on Excel. And these are the Barrett True-K, which is not my favorite, although I usually take a look at it. Haigis total keratometry, which is the combination of the regular Haigis, not the Haigis L, and total keratometry by the IOL Master 700. This, so far, is the best one. It is even slightly better than my love ray tracing with MS39. And then we have the new Offer QST that I have Dr. Offer to develop, which has also a post-LASIK calculator. What about the Barrett? I published a paper with Pentacam measurements some years ago, and the results were not so good if you use the Barrett True-K no history. Then Barrett wrote me an email. He was surprised by the bad results with just 50% of eyes with the prediction error within half a diopter. And we investigated against that sample, and we found that if you use all the historically available data, that is the corrected refraction by the laser and the posterior corneal curvature, the percentage increases up to 70%. So you know that when you go to apax.org, you have the opportunity to enter all this data. And the more information you add into calculation for the Barrett, the better outcome you can receive. And you know, for example, you can enter the posterior surface, the posterior power. And what about the Haigis total keratometry? Haigis formula is important because it does not predict the ELP from corneal power, as I told you before. So you don't need a double K version. Probably you already know what is total keratometry. Total keratometry takes the back surface of the back power of the cornea into account, and it does not suffer from the keratometric index error. And you can use the same constants as standard keratometry. A paper was published 3 years ago by Doug Koch and Li Wang showing better outcomes compared to Haigis L and Barrett True-K. But in my experience, we have 28 eyes, not yet enough to publish, and we have as many as 80% of people with a prediction error within half a diopter. And you see, okay, this is not updated here. There were 23 eyes, now there are 28, and the percentage is even better. And if you look, the Barrett True-K on average provides a myopic outcome, which does not occur with Haigis total keratometry, and the percentages are much better. And they are even close to those that we can obtain in long eyes without myopic EXCIMER laser. And now let's come to the topic you invited, that is MS39. This device merges two technologies, that is anterior segment OCT and Placido corneal topography. I think that you have the MS39, right?
Right, yes.
So you probably already know all these features. You can have a map with 25 or 12 meridional scans. I prefer to use the 25. All these images are merged to have the anterior and posterior data. We previously found that there's a very high repeatability of measurements and a good agreement with both Sirius and Pentacam. And how can we calculate the IOL power? This is very, very easy. You just have to enter the axial length after you did a scan, and you have to enter the IOL. And here comes one, I don't know which IOLs are you implanting from which manufacturer, but it does not matter so much. I saw what's important is to enter here the A constant of the ULIB website. And then you get the prediction. You can have also the prediction for toric IOLs, which is my preferred method to calculate toric IOLs after LASIK. To tell you the truth, I always take 3 measurements at least for one of these eyes, because the repeatability is not always perfect. And sometimes you get, for example, 19 with the first measurement, 19.5, then 19 again. And so I try to get at least 3 measurements with the same power. And I feel happy when this power is close to the power calculated by the IOL Master 700 with the Haigis total keratometry. What does ray tracing mean? It's something that is totally different compared to original formulas, because it ray tracing calculates the IOL power according to Snell's law using the refractive index of each diopter, air, stroma, and aqueous. So there is not the keratometric index 1.3375 that I talked about before at the beginning, and which is a source of error. Here, you don't care. You are not making any assumption about the power of the whole cornea, because you are not just measuring the anterior surface, you are measuring also the posterior. So all theoretical formulas, including the Haigis, are based on a series of false assumptions. The first they think that the cornea, they treat the cornea as a single surface, an infinitely thin lens. In fact, they are called thin lens formulas. And that's why we use the keratometric index. Also, the IOL is infinitely thin. And in addition, the predicted ACD does not coincide with the post-operative measured position of the lens, but it is rather the predicted ACD is a fictitious number that depends on the IOL constant. If you put the SRKT or any formula on Excel and you see where the lens is predicted to stay, you will see that it's predicted often to stay around 6 millimeters back to the cornea, which is impossible. So you can never make a comparison between the predicted ELP by theoretical formulas and predicted position of the lens by ray tracing, which is a thick model, thick lens model. So ray tracing calculates the radius trajectory based on Snell's law, the refraction index of each diopter, the corneal curvature, but also the asphericity, all the aberrations, the pupil diameter is not just paraxial. And that's why it's useful, for example, when you have decentered or irregular corneas, because you are not just basing your calculation on K1 and K2, you are considering all points inside the pupil. Of course, you need to predict somehow the IR position, and the CSO engineers did a good model for this. So ray tracing, in my opinion, is the most logical solution, because it's not based on any false assumption like the keratometric index. It's not limited to the paraxial optics, but considers also optical aberrations, higher order aberrations, and you don't need any historical data. This is a good advantage because you can use this software to calculate the power in eyes that underwent radial keratotomy after LASIK, after any other surgical intervention. You don't care. You just do the calculations. The main limitation for any ray tracing software is that you should know the physical properties of the IOL, the curvature, the thickness, the asphericity, and sometimes these are not, many times, these are not available. But if you just enter a generic IOL on the CSO software with the ULIB website A constant, it works sufficiently good. Well, of course, there are also other devices performing this ray tracing. One of them is the Sirius. We previously did a paper on Sirius back in 2014, and we found that we had 69% of cases within half a diopter, which is not bad. But now we published a new paper on 39 eyes with the MS39. And in this case, the axial length was measured by optical biometry, and we used the ULIB constants. And it was published a few months ago. And here I want to give you some practical advices. Because, When you enter the axial length by any optical biometer in long eyes, we know that we have the problem of overestimation. You probably heard about the one-cock adjustment for myopic long eyes. This was published by the group of Koch in 2011, and they provided us with this equation for the IOL master, so that when you had around a 30 millimeter long eye, using this equation, the axial length was reduced by around 1 millimeter, and it was proportional to the axial length. So when I started this study on the MS39 ray tracing, I wanted to see if it was better, more accurate to enter the original axial length from the printout, or the value which is adjusted by one-cock equation. And then there are also two adjustments that have been published by Holiday in JCRS January 2019, one for the Holiday 1 and one for the Holiday 2. These are polynomial equations that I did never have time to enter on Excel. Probably in 10 minutes, this could be sufficient, but they are available on the Holiday software, which I bought some years ago, and I renew my subscription just for having this value. And for example, you see in this table that down on the bottom that the 34 millimeter axial length is reduced to 32.6 with the Holiday 1 and to 32.9 with the Holiday 2 adjustment. So since these were the last numbers that have been published, I wanted to see how these equations work. And this is these are the polynomial equations, January 2019 JCRX. First of all, when you apply these equations, you see that the numbers change. For example, on the original printout, the axial length, the mean axial length in this group of 39 eyes was 27.79. Using the one-cock adjustment, axial length was reduced to 27.32. Using Holiday 1 adjustment, this change was less aggressive and it was 27.47. And using the Holiday 2, even lower, even less aggressive, 27.56. And these are the final results that have been published. Let's start from the original axial length, the one from the printout. What do you get? A mean prediction error of 0.56, which means that if you do not adjust the axial length and use ray tracing, you get a hyperopic mean error with just 38% of cases within half a diopter, very small percentage, very low. If you go and use one-cock adjustment for axial length, you go on the opposite, because you go to a mean myopic outcome. Okay, all the remaining values increase, but still not good. I don't like to have myopic eyes. I prefer to have ametropic. If you use the two Holiday equations, they give a very similar outcome. So you see that you have a prediction error which is very close to zero, and more than 70%, almost 77% of cases within half a diopter. And this is after I collected these cases and I had 76.9% of eyes within half a diopter. I took the decision to use this as my gold standard. So my gold standard now are two: this and Haigis formula with total keratometry. Here, just for a comparison, the Barrett values still based on the MS39 measurements, and you see that you are you have lower percentage of eyes within half a diopter. So this ray tracing is very accurate, is easy. You don't need any Excel file, you don't need any pre-op data, and the accuracy is equal or greater than all most reliable methods. Although it's a hard challenge with Haigis total keratometry. And before going to the last examples, I just want to tell you that since I showed that Holiday 2 adjustment was the best choice, CSO developed their own axial length adjustment, which I think is very similar to Holiday 2 adjustment, so that now you don't need the Holiday software. Once you have entered the axial length measurement by your optical biometer, you just have to click adjust axial length on the MS39 software. So axial length is proportionally reduced. So just a few words about Oculix, which is another software ray tracing available, which can be installed on almost all devices and gave quite good results. And now you have ray tracing by Olsen also on the Pentacam. Our preliminary data show that this is less accurate than MS39. That's all. So if you have any question, I'm here for you, or you may write me later. This is my email. Thank you.